Yes. Can I share my screen or do you want to keep sharing? Pranav, what do you want?
Anything
Up to
is
you.
fine.
Anything's fine, right? So, Harsh, let me present.
Okay, sure.
Yeah. Okay. Hi, everyone. Before we start, a reminder that we'll be recording this session. Uh, so I'll just get started. Pranav, you can start the recording. Sharing my screen.
Yep, done.
All right. Hi everyone, welcome to OTC Talks 6. But before we jump into OTC Talks, for the folks who are joining in new for the first time, welcome to our tech community. This community was started back in 2020, and it sort of started very naturally where it was COVID, it was the pandemic, and we started meeting every Saturday at 10:30 p.m. IST. And since then, yeah, I think we have been hosting OTC catch up for 202 consecutive weeks. So we recently touched 200 catch ups. So a huge congratulations to the entire community. uh, Moving on to just a little bit about a background on our events. uh, we have had OTC catch-ups, and of course we also maintain summaries for each sessions. While these summaries aren't minutes of the meetings, they are entirely resources, links, folks who joined, so folks who aren't able to join uh, get a good view about what the entire catch up was about. And we also have OTC talks that we started in December 22. I'll speak more about it. Otherwise, other than that, we have had in person meetups in the past and a few community collaborations as well. All right. So back to OTC talks. We started OTC talks to give catch-ups a direction, basically, so that folks can discuss whatever they have learned, something deeper in technology. And for people in this call who would want to give a talk in the future, it's very straightforward. Come to OTC talks and fill out the CFP. We will reach out to you and help you with anything that you require to prepare this talk. And finally, today we are here at OTC Talk 6, where the speaker, the man of the hour, is Harsh Kapadia, and he'll be speaking about ELFs. The title of the talk is all about ELFs. And a little background about Harsh. Harsh currently works at AMD as a field application engineer. He recently graduated out of Boston University, and he's one of the founders of this community, organizers, as he would prefer to say. And I'll let him take over now. Back to you, Harsh.
Awesome. Thank you so much. Everyone, just a reminder, this talk is being recorded. Yeah, without further ado, let me present my screen and let's get started. Okay. So I hope you can see my screen.
Yeah.
Awesome. Right. So hey everyone, we're going to talk about else today. Before we start, let me just tell you a bit about myself, although Tushar did. I'm interested in software and systems. Been doing that for quite a few years at this point, both uh, outside of work, just because I like it, and at work as well. What I'm looking to do is essentially go deeper in tools and tech. Previously, I've given talks on a few things like internals of Git, Mac and IP routing, CORS, and stuff like that. Currently, I'm an organizer at our tech community and a field applications engineer at AMD. If you want to know anything about me, please go to my website. So yeah, today's talk is essentially going to be around an hour or so, most probably in an hour. I'm trying to keep it at that mark. And everything that is going to be discussed today is already written in like text form or in full detail. So feel free to If someone can please paste this link in chat, feel free to go there. I don't think you need to take notes or anything. Just sit back, relax, pay attention, and ask questions. Right? Please ask questions. Feel free to interrupt me with anything after I finish my sentence. And yeah, I'm this talk is essentially me having learned something over the last few months, and I just want to share what I've learned. So again, I'm not perfect, and if there are any errors or mistakes, please feel free to let me know, or any clarifying questions, please ask me. I'll try my best to answer. Um, so yeah, awesome. So what are we going to do today, right? So there are five major things that I want to do. Well, four, but okay, five. Compilation steps, right? We'll talk about pre-processing, compilation, assembling, linking, right? All the steps of compiling a file. Then we'll talk a bit briefly on a high level about how a file looks like in memory, right? How a process looks like in memory, sorry. After that, once we have this sufficient background, then we can start talking about the ELF format, right? And after that, we start talking about how we can, like, once we know how a ELF file looks like, how do we examine it? What utilities do we use to actually examine files in real life, right? So I know the talk is about ELF, but to understand ELFs properly, or to understand why they have done things the way they have, there needs to be some context added with compilation and process memory layout. So for the first two agenda topics, please bear with me, right? We're trying to get to ELF, so we need to have some backup. Okay, so yeah, moving on, right? So first thing that we are looking into, compilation steps, right? So to so yeah, when we run a program, it's essentially we have a hello.c, right? And we use GCC, the GNU compiler collection, right? We run that GCC hello.c, and we get an output file that we execute, and we get the output, right? So this output file, right? This particular output file, that is essentially what is an ELF file, right? An ELF file, out of all the other file types that it supports, ELF is mainly the primary executable file on Linux, right? So when you're running any file on Linux, it is highly likely, almost always going to be an ELF file, right? So yeah, so this is that ELF file that we're going to talk about today, right? What is the format of this file, and to get from this to this, how does that actually happen, right? Because this compilation step is actually there's quite a lot of going on behind the scenes, right? So we're going to take a high level look at what is going on here, right? Okay, so just to show this format in the command line way, nothing very different. So yeah, I have hello.c, which has a printf hello world line in it. I compile it, right? So now I have this a.out file, right? And just to inspect what kind of file this is, there's a command on Linux called file, right? So file a.out gives you that, hey, this is an ELF, right? And all this other output, we'll look into this later, so don't worry about it. So for now, just know that, oh, okay, this is an ELF file, right? And then I just execute this output file, and we get our hello world, right? So just a simple view on this, right? Okay, so what actually happens in this compilation step, right? What is actually going on behind the scenes, right? So at a high level, what is going on is, so when you have your hello.c program, right, your hello world program, and you say, okay, GCC compile, it goes through four main steps, right? Processing, pre-processing, compiling, assembling, and linking, right? And then finally, when you actually execute the file, the loader comes into play, right? So loader is not part of the compilation step; it's more part of the running step. So yeah, these first four are the steps for compiling. Now, what happens in each stage, right? And we'll take a look at this as well on the command line right after this. So yeah, so pre-processing, right? So you have your hello.c program. The moment you start compiling it, it first goes to the C preprocessor. What this does is, essentially, when you have header files that you've included, or a certain global variable that you've defined in a header file, right? Or a or a function macro that you've defined, or anything like that, it'll all compile all of it into, not compile, sorry, it'll pre-process all of it into one file, right? Now, I understand that's confusing to understand. That's okay. We're going to see this in practice in just a few moments, right? So just hear me out for now, right? So initially, hello.c gets pre-processed to hello.i, right? That's a .i extension file, right? We'll see what each file has in a bit, don't worry. After that, this hello.i file is compiled, right? So when it goes to the compiler, what it does is it generates assembly code, right? So, and that generates hello.s, right? .s is usually an assembly file, right? So it generates some assembly code, right? Again, we'll look at this file in a bit. And then it goes to the assembler. What the assembler is essentially doing is converting, depending on what architecture you are. Let's say you're on an AMD machine, Intel machine, or let's say you're on a completely different architecture like a ARM or a RISC-V based architecture, right? So they'll have completely different ISAs, right? Like completely different instructions that the CPU understands, right? Or the CPU can interpret, right? So it'll generate object code, also called machine code, right? So that's what an assembler does. It takes your assembly and converts it into machine code, which is essentially instructions that the CPU can understand, right? Um, so so once we have that assembly, we have that assembled, we have that object file, right? So it has a .o file extension, right? And this file, by the way, is also an ELF. We'll look into it later, but just so that you know, this .o file, object file, right, is also an ELF file, by the way, right? So now now the next step is linking, right? So what the linker does, it takes your machine code, right, and it will add all the libraries. Let's say you said printf, right? So or you've had any other function from other file that you've imported, right? So what your linker will essentially do, be like, okay, out of all these files, because it has to create one file, right? You've included functions from different files or whatever, and it has to create one file at the end, right? So that's why it has to kind of figure out, okay, I have this object file with me, but this file references loads of other different files as well, right? So how do I let the loader know or let the program know that, hey, there's different places you have to go to fetch different things, right? So that's what the linker does. It takes multiple object files, figures out okay, where do I take this function from, which library has it, and how do I link it and stuff like that, right? How do I get everything together in one file so that that file can execute properly, right? And not cause errors or runtime faults, segmentation faults, because the correct function was not found, right, at runtime. So that's what the linker does, right? It creates the final executable file. This executable file is also an ELF, right? We saw it right now, right, in this step here, right? This a.out file is also an executable, right? So this is the final output, right? So when you go from this to this, you're pre-processing, compiling, assembling, linking, and finally you get this file, right? And then when you actually execute it, right, the loader first. So finally, this is, you get your executable file, right? And it's stored on disk, right? Your a.out file, right? And then when you start running the program, the loader is like, okay, let's start putting this entire binary into memory, right? And it starts putting it in the RAM, right? And so now we essentially, before we look at how it goes into RAM, we essentially need to look at compilation, right? What happens in these steps? What is going on in each step, right? So we're just going to take a high level look at that. Before that, I'm just going to stop for any questions if anyone wants to ask anything. Awesome. Okay. So let me just go to this. Right. So there's my terminal. Right. Let's just create a directory. Elf. Oops, sorry. Okay. So let's get a simple file in here. Oh, sorry, missed. And also, let's also get the header file here. Right. Okay. Now let's look at what is going on in these two files, right? We have this, and let's also do this. Okay, so we have two files, right? On the left, you have main.c, right? And on the right, you have main.h, the header file for that. Is this a font size enough for everyone? Can everyone see this?
Yep.
Okay, great. So, okay, what we have here, right? So let's start with main.c, right? Because that's the program that we're going to essentially run, compile, right? So, okay, we have a main function. This main function is calling a macro, right? This macro is just essentially taking a string in and just putting it in a printf function, right? It's just a macro for a printf function, right? So essentially, what I'm doing is in main.h, I have two variables, like three variables defined, right? Two hash defined ones and one constant variable, right? So I'm just referring to those. And how this works is these are called there's something called macros or preprocessor directives or something. I don't remember the exact term, but so what this is doing is, okay, if this particular symbol main underscore h is defined, only then will you know try to do this. If it's not defined, if main underscore h is not defined, right, then just say variables not found, right? So in my header file, if you see here, I say hash define main underscore h, right? So if this main file header file is included, right, I am able to access these particular. I define this, and because I define this, it goes into this particular block and not this block, and it's able to access these values, right? So this is the basic simple setup that we have for main.c, right? Now let's start compiling, right? Let's see what happens. And just to show you what how it compiles, I'm just going to do this. Um, okay. Just to compile it, right? This is main.c. We have this a.out file. I run it, and we get this is global var, like, right, that we had defined in main.h, right? This string, and we also get the value of nice var 69, which is 69 itself, right? So yeah, now let's go over each step, right? Each step in this process. Where did you go? Here, right? Each step in this process, right? Let's do this. Now, the first step is pre-processing, right? So what we can do, we can tell GCC that, hey, I only want you to pre-process stuff, right? And I'm going to say for main.c, right? And I'm going to put it in a file. Otherwise, it's just going to give me a huge output. Let's call it main.i, right? Because if you remember, the output of a preprocessor file is hello.i, right? So I'm just naming it main.i, right? Okay. So, oops, I'm sorry, my bad. I think, oh, sorry, it's e, my bad. It's not hyphen I, it's hyphen e. Okay, right? So now let's inspect what is in main.i, right? Let me do it on this side, I guess. Right. So again, I know this is confusing. Bear with me for a moment, right? So this file has so many lines, right? You can just see whatever it's doing, etc., 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 right? And as we keep scrolling down, right? Finally, at the end of this file, right? Right. So we wrote like a 10-15 line program, and this preprocessed file is 700 lines, right? 750 lines, right? So, and we have our stuff here or whatever, right? So just to make this process a little less complicated or to not confuse you with so many lines, what is essentially happening is, I'll show you what's happening, right? Let's make it easier for ourselves. So I'm just going to add a flag to remove no standard to remove any standard includes like stdio.h, right? Just to show you, in main.c, I included standard io.h, the header file, right? So that is what is adding so much stuff to, here, right? So I'm just going to remove that so that I'm able to actually tell you what's going on, right? So I'm just going to name that main. No standard. Oops. No standard includes. Right. Okay, that's okay. Wait, let me pipe that in as well. Anyways, right. So now let's open that file. Oh, I can't type. Sorry, that's the nerves. What? Uh,
The
huh.
spelling, I think.
I mean, it outputs to main, but oh, my syntax is wrong. Oh God, sorry, this is just knobs. And yeah, spelling as well. Thank you, Pranav. Okay, now this should work. My bad. Finally, okay. So now let's figure out what is going on, right? Open, right? Okay, so here if we see, we remove standard stdio.h, so it's not able to find it. That's why it's giving an error, right? So let's ignore that for now. So the two files that we care about is main.c, right? Main.c that we wrote, and main.h, main.h, right? These are the two main files that we care about. So after pre-processing, let's see what happened, right? So this was main.c, right? This is what it looked like, right? Now, what it currently looks like after pre-processing is this, right? So essentially what pre-processing did is it first figured out, okay, do I have access to main.h? Yes, I do, because main.h was referred to at the top here, right? It was included, right? So because it found main.h, it was able to see, okay, main.h is defined. So now because it's defined, it went inside this uh, block, right? And replaced this function macro with the actual text, right? With the actual function, right? So that's why you see printf %s here, right? And it was able to find global var, right? If you see here, global var was placed right above this, so it included it in the same file, right? Although here it's two different files, right? Global var is included in main.h. So when you pre-process something, it gets included right in the same file, right? And this string 69 that you were able to see here, which was a hash define, right? That directly just gets added here, right? So just wanted to show you how pre-processing essentially just removes these hash defines and replaces it with the value, right? These pre-processing directives are also removed and replaced with the actual value, right? And this function macro is also replaced, and you get in the final pre-processed output, you get it's replaced, right? So just wanted to show that to you, right? Um, okay, so any doubts with this? Anything that you don't understand or any questions? Awesome. Great. Um, okay. So now that we know what's happening with in 4 hours, okay, fine. Yeah. So now that we know what's happening with pre-processing, right? Let's go to compiling, right? So to compile, what we tell GCC is that let me get out of this. I'm going to tell GCC, okay, hey, GCC, please compile, right? I'm only going to compile. Let me check the flag. Oh, it's -s, my bad. Right. So just compile, right? And I'm going to use our main.i file, right? Because that is the file that's generated, right? Preprocessor, and then -i is the preprocessed file. So I'm going to use the preprocessed file, and I'm going to tell main GCC that, hey, just compile this for me, right? Okay, it's been compiled. Let's see what happened, right? So we now have this main.s file, right? So if you see here, whatever is the output of the compiler is anything .s, right? So we have this main.s file, right? So this, if you remember, is going to be assembly, right? So again, just to show this to you, main.c, no, main.s, sorry, right? So this is what you get, right? Your move instructions, move a quad, move q is move a quad word, which is, Pranav, correct me if I'm wrong, that's 16 bytes, whatever, right? So quad word, double word, and stuff like that. Right? There are different things in assembly, different sizes. So yeah, LEA stands for leave effective address, and stuff like that, right? So you have different instructions, right? Is return and stuff like that, right? So you have assembly, right? So this is the compilation step, right? And just to show you a different, so this is for, I'm on an AMD machine, right? So this is going to be at the AMD 64 or x86 64 architecture that this code is compiled for, right? But again, there is another architecture, right? One of the architectures that exists is the RISC-V architecture, right? So I just wanted to, I need to, okay, wait. I just wanted to show you how that assembly looks like, right? Okay. I need to go to the branch. Awesome. Okay, which file do I want? Okay, I found it. Main hyphen disk5.s, right? So this file, if you compare the same section, it's going to be completely different, right? So if you saw, right, so instructions are completely different. It has its own way, it has its own flavor of assembly, right? It's doing the same thing, right? The final action is the same, but just the way it achieves it is different, right? It has its own way of doing it. This is RISC-V. In case you want to look it up, just look up RISC-V, right? It's part of the RISC type of stuff where AMD 64 and stuff like that is CISC, complex instruction set computing. This is reduced instruction set computing, different architecture. Anyways, right? So that looks completely different, right? So JR is jump right, LD, I forgot what, MV is move, call is it's calling a function, right, etc., right? Okay, so that is your compilation step, right? Depending on your architecture, it will generate different assembly code, right? So we are at hello.s right now. The next step is assembling, right? So for assembling, if you remember, it is converting that assembly code into something that the CPU actually understands, right? Which is machine code, right? Or object code. So machine code, right? So again, if I remember, that's C, right? Now let's take our main.s file that we generated and tell the compiler, compiler that, hey, I just want you to assemble this file, don't do anything else, right? So I hit enter and we see what's up and we get this .o file, right? This is an object file. And just to show you what kind of file this is, I'm just going to use the file command on Linux. And if you see, main.elf is an elf and it's of a type relocatable, right? It's a relocatable object. We'll get into relocatable stuff later. Don't worry, right? For now, just know that, okay, it's an elf, right? So yeah, what we did right now was we took assembly code and compiled it to an object file, right? Which has machine code. Now let's see what this file has. We want main.o, okay? Gibberish, right? We are not able to figure out what is going on here, right? So, by the way, just see these strings, right? We're going to look into these strings later on, don't worry, right? Okay, so to figure out what is going on in this file, I'm just going to do this. I'm going to use xxd, or you can use hexdump as well, and it's a hex editor. See what it does, right? So let me do this for now. Right, so this is just dumping out the raw contents of the file as it is, right? So this is the address here. Oops, my bad. So on the left here, this is the address, right? This stuff. Okay, wait, why is this not? Yeah, this stuff is the address, and then like the base address, and then you have to add 0, 1, 2, 3 as you go along this line. But yeah, and this is the actual content, right? This stuff 7f 4 5 etc is the content, right? And this is the ASCII representation of that. So on the, no, I do not want to turn on sticky keys. So this is the hex dump, right? This stuff in the middle, right? On the right, you have the ASCII output of that same hex value, right? So every two numbers here is 1 byte, right? 7f45 45 stands for E, right? In ASCII. Let's just check the ASCII table. Again, I don't need to do this, just out of curiosity or just to show you. If we go to x45, right, 45, right? And the ASCII representation of that is E, right? So which is why here for 45, which is the second byte, oh God, you see an E here, right? So for 45, which is the second byte, you see E over here, right? So just to kind of show you. So yeah, this is what your main.o has internally, right? This is the raw output of it. Again, we're going to, because it's an ELF file, we can understand the structure of this file, and we're going to understand the structure in a bit. So yeah, this is what it looks like. Again, RISC-V will have its own thing, right? And to give you a better example, I'm just going to open my browser. I should have kept this open. Let me use this. Right, to show you what machine code actually means, right? So this is an output of one of the functions, right? Which is, so, okay, wait. Let me make it simpler. So what we've done till now is essentially we've generated the object file, right? So we went to pre-process it, we went to compile it, we went to assemble it, right? So we are there till assembling, right? We saw this object file, it's an ELF file, we've done that, right? Okay, so we are till here now, okay? Before we go to the linking step, I want to essentially so we assembled this file, right? So there is something called disassemble as well, right? So you can use machine code, right? So this code, you can just see these bytes here, right? And you can use these bytes to go back to the assembly, right? So to do that, there's something called object dump, right? Which disassembles the file for you, right? So object dump -d and main.o. Oh my god, this is going to be a problem. Anyways, I'll use this instead, right? So if you do this object dump -d main.o, this is the output that you get, right? Now what is going on over here, right? So we are getting back that assembly, right, that we saw in main.s, right? We're getting that assembly back, almost that, right? And here what we can see is how the CPU is interpreting your assembly, right? Like what is going on. So what is going on is essentially each of these lines is an instruction, right? So what 55 means, right? Your CPU understands 55, it doesn't understand what push %RBP means, right? So when we have our when we've compiled a code to assembly, and when we finally assemble it to machine code, right, it goes to 55, because as per Intel or AMD architecture, right, the architecture that's defined AMD 64 or x86 64, right, push is supposed to be translated to push, this particular value is supposed to be translated to number 55, right? Hex number 55, right? Because when CPU sees 55, it understands what this means, right? And it is able to do this operation, right? And this value here is called an opcode, right? An operation code, right? And this is the instruction that your CPU understands. Similarly for this, right? So 48 is your opcode, right? And again, this doesn't completely translate to 89 being this value and E5 being this value. There's a very complicated thing that I was not able to get into completely, right? So this particular instruction translates to this, right? And the CPU is able to understand that, right? Exact translation, there's an entire process for it. There's a 1 or 2 hour video to if you want to look it up, I've linked it. But I didn't have the time to essentially get into exactly how the translation works, but there is a translation, right? So these numbers are actually defined in what do you call it, in the Intel Software Developers Manual, right? Just to show you. So this is a 5,000 page document, by the way, which has everything related to the processor, right? To the architecture, sorry, instruction, everything. We need a very specific part of this, which should be, okay, let me download the individual one, which should be in volume 2A, right? So I just downloaded a subset of this. And if I go to, and if it loads, okay, thank you. Where are you? I should have kept this ready. My bad. 512. Okay, I don't think I'm going to find it right now exactly, but yeah, it's there. Believe me, right? Um, so yeah, this translation actually exists in these manuals, right? It's properly defined in the software developers manuals, right? It's very properly defined. Okay, so that is essentially what is going on in the assembly thing, right? So it generates this machine code which the CPU is actually able to understand, right? And which is why it's able to execute stuff. Okay, so we went from um, so your code essentially went from this, right, to this, to this, and then finally to this, right? So right now we are at this step. Okay, so C to pre-processing to compilation to link to assembling, right? Now we go to linking, right? Where is my presentation? Here you are, right? So now we go to the linker, right? What we do here essentially is we just take all of these files, right? We take our hello.o or our main.o file and essentially compile it into an executable, right? And to do that, it's our normal command, which is essentially just being like, hey, gcc main.o, and we compile that. And if we check, we have our a.out file, right? And again, if we do a.out, we get our execution, right? So this was just a look at, and obviously if we check, we already saw it, but yeah, a.out is an, oops, my bad. A.out is an elf file, right? So yeah, okay. So now that you've seen how this works, and the fact that, okay, the assembler generates an object file which is an elf file, and the linker also generates an executable file which is also an elf, right? So we've realized that elves are, right, for now you realize elves are two types of files: object files as well and executable files as well, right? Your binaries. Okay, now we get to actually running the file, right? When we run the file, before it can actually run on the CPU, it needs to get put into RAM, right? So that the CPU is able to access whatever instructions it needs and stuff like that. The instructions are now machine code, right? That we saw. So, so to let the CPU access that file, right, to run the program, we need to load that program from disk to RAM, right? So to get to disk to get to RAM, right, you can't just dump the file into RAM, right? There's a certain way you have to put it in RAM, right? So that's where we look into process memory layout, right? So this is it, right? Almost every process on your every process that you run or whatever is going to kind of look like this, right, in RAM. So what is going on here, right? This is the address space of your processor, right? This is where sorry, of your process, right? This is where your program is running, right? And all your data, everything that you're doing, everything that it needs for execution is all over here, stored over here, right? From top to bottom, this is the top of the address space, and this is the bottom, right? um, Okay, so what's going on here, right? Just a quick brief overview, right? You have the kernel up here, right? It's always mapped into every process, right? Wait, I'll tell you why. Calm down. So, so you have the kernel at the top, right? And then you have a stack segment. You have certain while it's running certain shared libraries like your libc C library, right? Libc that is mapped over here, right? Then you have your what each segment is doing. I'll tell you. Just for now, hear me out, right? You have your heap which grows upwards, right, in the memory in the processes memory layout. Then you have the BSS segment, you have the data segment, and you have the text segment where your code resides, right? Okay, so now what are each of these things, right? Let me start at the bottom, right? So at the start of your process's address space, you have your text segment, which is essentially where you have your machine code, right? All your instructions go in here, right? So this is what your text segment is. Then you have your data segment, right? Data segment is where all the variables that you initialize. So let's say you say int I equals 5, right? So that data will be stored over here, right? And let's say you had another variable which was just int I. You didn't give it any value, right? It was uninitialized, right? You just said int I. So those kinds of variables are going to go in the BSS segment. Now, why are there two different segments? Why can't it be in this? Because they're variables, right? Int I equals 5 or int I or whatever is just a variable, right? So why is it separated out into two different segments, right? The reason for that I'll tell you later. Just bear with me for now because it relates to how things are stored in an ELF file, right? So yeah, for now, just know that, hey, data segment has statically allocated variables which are given values. So um, uh, if you have an array of 3 variables and you say array equals 1, 2, 3, right? So that's an initialized variable, right? That will go in the data segment. But if you just say array 3, right, it will go in the BSS segment, right? Because you're not given the array any value, right? You just said, okay, I'm going to have an integer array of 3, right? 3 variables, right? But I've not given you the values. So those go in the BSS segment, right? And anything in the BSS segment is initialized with a 0, right? So those are these 3 segments. Then we have our heap, right? With the heap, the heap is used for any dynamically allocated memory. What does that mean? When you do malloc to essentially get memory. So let's say you say you want to create have like 5,000 bytes, allocate 5,000 bytes whenever a function is called, right? So what you usually do is int star array 5,000, and you say malloc give me 5,000 bytes, right? Whatever, right? Or char star array and malloc 5,000 bytes, right? So give me 5,000 bytes. So whenever you allocate memory on the fly during the program, use malloc, calloc, and stuff like that. That time you're using the heap. This is where your memory is getting allocated, right, on the fly. And then whenever you have, again, dynamic linking is something we'll get to later. So this I'll explain what is going on here later, right? So so yeah, now here your stack is very important, right? Because stack is essentially where all your functions are getting in, right? So when you make a function call, right, you say, okay, I should have had a figure to show you that, but okay. Anyways, so when you essentially call another function from inside another function, you have a stacking mechanism that takes place, right? Does anyone not know what stacks? Do you want me to explain that further, or do you understand what I'm saying? Because I should have had a figure that's missing. I can show it to you. But if anyone wants more details, let me know. Okay, I think people understand what a stack is. If anyone doesn't know what a stack is, please let me know so that I can. I wish, not really, Bhavesh. No, it's not a stack. But yeah, if you don't know what a stack is, please let me know. Right, all your function calls get stacked here, one after the other. Right. And when you return from a function, one of a stack frame gets popped. When you call a function and you go inside the function to execute something, a stack frame is added onto the stack, so it grows down, right? Stuff like that. That's what the stack does, right? So stack is the function calls, heap is for dynamic memory, BSS is for uninitialized variables, data segment is for initialized variables, text segment is where you store your code, right? And then at the top here, for every process, you have the kernel mapped here, right? And the reason it's at the top here because Linux is called a higher half kernel, right? So what it does essentially, every process has the kernel mapped inside the process itself, right? So what is going on here is why is the kernel mapped into every process, right? Like, isn't that not good? But actually, that brings me to something called virtual memory, right? So what happens here is essentially the kernel is not actually mapped here, right? I mean, okay, let me rephrase that. So what's going on here essentially is the kernel is mapped to every process, right? And why is that so? Because it makes it easier to make system calls, right? Now, system calls could be reading a file, writing a file, and stuff like that, right? Or accessing a particular device or whatever, right? Input, output, stuff like that. So to do all of those things, you need to make a system call, which is in the kernel space, right? So that's why, to make it faster, to not switch context from one program to the other, you just map the kernel pages right into the processes memory, right? Now, one question could be, okay, if the kernel is mapped in the processes address space, can't the process make changes in the kernel? Like, it's in the same memory address, right? The point is, it can't do that, right? It can't do that because this space it actually has permissions, right? So the process can't actually modify stuff here. There are permission bits that are set on set in pages and stuff here, which essentially said, okay, you have access to this, you can read stuff or you can call functions from here, but you can't modify stuff here, right? Which is why mapping the kernel space here is okay, because permission bits is what prevents the process from actually messing around in the kernel space, right? It can only mess around in this space, which is its user space, right? So yeah, which is its process space. So yeah, having the kernel space here is not a security problem. It is actually more convenient and more efficient for the program, right? Otherwise, if this was not done, you would have to make a proper context switch to a different to the kernel mode, and to the kernel program, and that would take much more time for every system call that you make, right? So, okay, that is the high-level view of a structure of a process in memory, right? Um, so, yeah, and BSS data and text is something we're going to see in the ELF format, which is why I needed to go over this as well, right? Any doubts? Anything you want to know till now? So in the text segment, Viranchi, we have our machine code, right? We have essentially the program that we want to run, right? The machine code that I showed you, that is essentially what we have. This stuff, right, is what we have. All of this stuff. Okay, not all of it, but like the main instruction. Sorry, where is it? So this stuff, right? Your program, the main part of your program. This middle stuff is what we have in there. There was another question. Are all codes in the same place? Depends, but yeah, all, like if it's a dynamic library that you're calling during runtime, like maybe libc.so or something like that, that will not be in this in here, right? But anything that you functions that you define or you write properly or whatever, that is all that will all be in the same text segment, right? Yeah, we are not getting into pages, Viranchi. That granularity is not required right now. It'll just get more confusing, right? Which is why I was avoiding talking about space, about pages and virtual memory and stuff like that. I was trying to avoid, but yeah. Okay, any other questions or anything like that? Okay, great. So yeah, we can now finally move on to share. Oh, not share, my bad. Slideshow. We can now move on to okay. So this is not, so if you don't understand this, that's okay, you don't need to, right? This is not vital to the talk, but I just wanted to mention it for clarity's sake, or for those who understand what it means, right? It's not important to understand for the talk, so don't worry if you don't get it. Not important at all, right? For now, for this talk, right? To understand the talk, it's very important as a concept, but not important for the to understand what the talk means, right? So yeah, we're talking about each process having its own address space and stuff like that, right? And that seemed contiguous, right? This seemed like a contiguous thing in memory, like it'll be 4 gigs or whatever of continuous memory and stuff. But this is virtual memory, right? These are virtual addresses on actual RAM, like on your physical DIM, right? It will be in completely different places, right? It just logically appears to be in the same place, and the operating system translates these virtual contiguous addresses to the actual place in memory, right? Like physical memory. So yeah, there's just an address translation that goes on between virtual address space and physical addresses, right? So yeah, for people to understand what it means, yeah. And if you see, by the way, the kernel is just mapped once, right? And every other process has that mapped into the virtual space. So we're not constantly repeating the code of the kernel and stuff like that, right? So yeah, just wanted to let you know. If you don't understand it, it's fine. Not important to understand for this talk, right? If you just understand what this means, more than enough. Okay. So any doubts, any clarifications that's required? So doing strings main.o on files reads or whatever string. I am not sure, Alpesh. I'm not sure. We can actually check that because I'm going to cover utilities later on. Good question, though. That is something that didn't strike me. Interesting. Nice. Okay. Um, good one. Was kernel stay same regardless of process? I think so, Viranchi. From whatever my knowledge, till wherever my knowledge goes, I think so. It stays the same. Your OS and kernel. Um, yeah. If anyone knows better about that, please let me know. Okay. Awesome. So now we can finally get to F format, right? Maybe Viranchi. I'm not sure. Maybe the kernel changes or stuff changes, right? Okay. So now we finally get to the ELF format, right? What is an ELF, right? ELF stands for Executable and Linkable Format. That's the full form. It is the primary executable type on Linux. It essentially defines a particular way in which a file should be structured and how information should be stored, right? And yeah, so it first appeared in System 5 in I think 1984 or something like that, and it was adopted by Linux later on. It has not changed since the early 2000s, which is crazy, right? If you go and see all the official documentation, it all dates to like 2001, 2000, 1998, and stuff like that, right? So it's pretty much been constant since then. So the person who designed the format, like they had so much, like they had thought about it so well that they didn't have to change that format, right? Or yeah.
Actually, Harsh,
Yes.
the ELF format was unmaintained for a couple of years
Okay.
due to
Interesting.
legal issues.
Due to what?
Legal issues,
Oh,
ownership issues.
interesting. I
It
didn't know that.
changed owners a couple of times because the company maintaining it sold its copyright to a different company, and there was a whole lawsuit about it.
Hmm.
I'll share a link to my source for that.
Yeah, please. Interesting. I didn't know that. Nice. Yeah, people, if you have anything to say or whatever, feel free to jump in, right? No problem at all. Thanks, Siddharth. That was nice. Okay. So there are two formats of ELF, 32-bit and 64-bit. We are only going to focus on the 64-bit formats, right? And all the outputs that we've seen till now, like if we check any out, oops, sorry, my bad. So if we check any of these outputs for file main.over, whatever, for file main.o or a.o or whatever, it's always says 64-bit here, right? So we are only looking at the 64-bit ELF format because 32-bit is not like it's not that used right now. So yeah, we're going to look at the 64-bit format. Most of it is the same. For 32-bit, it's the structure is almost the same, and it's just the sizes of variables differ, right? Because it's a smaller addressing format. Anyways, so there are 4 file types that I was able to find online that have ELF that follow the ELF format, right? We've seen 2 till now, which is executable files. That our a.out file was an ELF, and our object file.o file was also an ELF file, right? So, and the other 2 file types are shared objects like libc, right? libc.so, your C library, and core dump files are also ELF files. Core dump files are essentially generated when there's a fault in the system, like a seg fault or anything like that. You can have a core dump file which gives you details about the CPU and stuff like that, right? I'm not exactly sure what a core file has in it, so yeah. Okay. So just to show you a few outputs, we've already seen these, but now we can essentially take a closer look at what the output essentially means, right? So this is a normal file that I'm just using a file command to execute to look at. It's an executable, right? So it's an ELF. It's a 64-bit ELF. It's least significant byte arranged, right? That's how it's arranged: little endian, big endian. That's the thing, right? So least significant bit first is the thing. PIE stands for position independent executable execution. We are not getting into PIE or PIC right now. I have personally not looked into it as well. It's an executable file, right? It's built for the x86-64 architecture, right? Then version 1, because as I said, ELF has still not gone to version 2 and stuff. And it is dynamically linked, and it is not stripped, right? Just bear with me and just just note these things, right? again, a different file, IL64-bit executable x86 architecture, dynamically linked, but this time it's stripped, right? What stripping means, we cover it later on. Just wanted you to note that there can be differences, right? Another file, we have another one. It's an ELF, it's 64-bit executable x86 thing, but this is statically linked, right? This was dynamically linked, this is statically linked, right? And this is not stripped, right? So this is the difference. It's statically, and previous two files were dynamically linked. Now there's another file, a.out, and this is a RISC-V file, right? So again, as 64-bit executable, but instead of the x86 architecture, it's compiled for the RISC-V architecture. UCB stands for, by the way, UC, University of California at Berkeley, because apparently they were the ones who defined it or whatever. So UCB is that university's name, but yeah, RISC-V is the architecture, right? So yeah, just wanted you to note that it's a different architecture than x86 that we're used to. Other file types, these are shared objects, right, are the main mother of all files, libc, right, mother of all libraries, libc, the C library, which is an ELF, but this time it's instead of it being an executable, it's a shared object, right? And same thing other than that, x86-64, dynamically linked, stripped, right? Again, now this is a normal object file that we've seen, right? At 64-bit, it's called relocatable, right? Because you're during assembling and linking and stuff like that, there is a lot of relocation going on, right? Because the assembler, the linker essentially has to take multiple files and arrange them in a proper order, right? To create one executable file, right? That's why it's called a relocatable file, because the executable can, so the linker can link these files or put them in the correct order, right? To make one final executable file. And then this is a core dump file. And you can just see that I have 64-bit LSB core file, right? So that's a core dump file. And I think I generated this file by creating a seg fault, or changing a flag in Linux, and then like in the operating system, and then like creating a seg fault with a C program or something like that. So yeah, you can also create it. It's pretty simple. Okay, this, and then okay. Now we get into the structure of an ELF file, right? And I think you can see some things that we've seen before, right? Text, data, and stuff like that. So anyways, so at a high level, the structure of an ELF file looks like there's a file header. Then you have, again, we'll go over each of these, so don't worry, just hear me out for now, right? There's a file header, there's a section header, there are segment or program headers, and there are sections and segments, right? Now, let's go over the file header, right? And don't get scared by this. This is just, just how it's defined, right, in the standard. So you have your file header, which gives you information about loads of things, right? So if you saw the file, so if you saw this file output, right, how is it able to know that, okay, this is a 64-bit ELF, this is LSB, this is a position independent executable, and then it's a type is an executable type. It's for this architecture, this version. What is the linking type, etc., etc. How is it able to figure these things out, right? Like, how is this file command able to figure things out? That is because your that is because the file header stores all of this information, right? And Wikipedia has a really nice table where it tells you, okay, what is each. Oh God, I searched for ELF and it went to you went supernatural being. I'm so sorry for that. Oh God, my bad. Yes, this is what I'm looking for. Right. So this is the file header, also called the ELF header, right? The file header. And if you see this, here is where you're able to see that, hey, each of these bytes actually means something, right? So if I show you sys5, right? How is it able to say sys5 here in the file output, right? It says sys5, right? How is it able to figure that out? Because the file header essentially tells you that, okay, if it's this value, it's system5, right? Similarly for your x86-64, right? If you see, where did it go, right? If you see 3E in a particular field, right, it should be AMD64 or x86-64, right? And to show you that the raw version of this also looks like this, I'm just going to show that to you. So this is the program that the parser that I built, right? right? So this is the output, right? So if you see machine, that's 0x3e, right? And if I see the value for machine, 0x3e, the AMD 64 or x86 64 output that we were seeing, right? So that's how you essentially figure out what's going on, right? Then if you see something like ABI version is 00, right? So your ABI version being OS ABI, right? Being 00, it makes it system 5, right? Then you have an important one, which is type, right? 0x03, like 03. So your type is 03, which makes it a shared object. What? That's weird. Should be 02, but interesting. Huh, interesting. Okay. I'm not sure why it is 003, to be honest with you. Okay. Um, interesting. Version 1, entry address, blah, 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 right? So yeah, there's some more stuff that your elf header also gives you, which we'll get into later. But yeah, just to let you know, this is how file essentially is able to figure things out, right? Another important thing is how do you figure out that this file is an elf file, right? When you tell the OS, okay, run this file, how is it able to figure out that this file is an elf file, right? The way it is able to do it is using something called magic bytes, right? What are magic bytes? They're just few bytes at the start of the file which indicate which file type it is, right? They have to be certain bytes for it to be like, okay, this is elf, right? This is an elf, or this is XYZ format, this is ABC format, whatever, right? So in the case of elf, you check the first 4 bytes of the file, right? If the first 4 bytes of the file are 7f, 45, 4c, 46, which is essentially translates to 7f and ELF, right? If this is what the first 4 bytes of the file are, then this is an elf file, and you can use an elf parser on this, right? So to get you back to the hex dump that I had done, to show you the start of the file, if you see this 7f45 4c 46, which essentially translates to 7f and ELF, right? So that is why this file can be used by an elf file. They are called the magic bytes, right? So every file has this, every executable has these particular bytes that you have to check for before you can be like, okay, I can use an elf parser on this. So if these 4 bytes are not these exact same bytes, you would be like, okay, I can't use this file. I mean, I can't use an elf parser on this, right? So yeah, that's also in the elf header, right? So yeah. What else? So after this, we have the section header, right? Again, section header will give you some information about the section, right? What is the section we'll get to, don't worry, right? So, okay, section header, right? To show you what it looks like, we go back here, and these are section headers, right? It's giving you information about each section, just to show you some sections that you've already seen before. Where is it? Where is BSS, right? See, wait, your data section, right? So this is the data section. Again, wait, let me show you. Okay, let's see what the sections are for Vim, right? Let's go to the binary of Vim and see what it's like. Okay, so the Vim executable, right, has these particular sections in it. And if we go and check for stuff, .text, right, your code, it's saying, okay, your code resides at this particular address, has this size, and it gives you certain flags, right? A and X. What do A and X stand for? A is allocate, X is execute, right? So you can actually execute this particular section, right? So there are certain flags that it gives you, certain permissions. It tells you which text it is, which section it is, what type of data it holds, right? So RO data is read-only data, where if you have a string, that's where it's stored. Your data section is right here, right? The 26th one. And then the 27th one is the BSS section that we had seen, right? Where all the variables are stored in these two sections. So, and there are multiple other sections as well that you have to parse and look into for stuff, right? Your dynamic library stuff is all here, right? Dynamic strings and stuff like that. So yeah, and these RELA stuff, these are all the relocation things that we were talking about initially, right? So yeah, essentially section header gives you information about the section. The section is where the actual data is stored, right? So yeah, your elf file, your elf header tells you, okay, your section header section header table is located at this particular address, right? This offset into the file. So then you go and parse this particular header, and then you'll be able to be like, okay, this much into the file or whatever, I can go and find the actual data for this particular section, right? So it's just a way to go and actually find the section, right? The section has the actual data, right? So file header tells you where you can find section headers. Once you find section headers, you can look for the particular section you want, and through this header, you can go and actually point in the file and be like, okay, give me this data, and using the size variable, you can see, okay, from this address, give me 10 bytes of data or 15 bytes of data or how much ever is the data, right? That's how you actually get your data, right? And to show you that you can actually get your data, I'm going to use something called, so readelf. Readelf is a Linux utility. Let me just clear this for you. -x, and let's see what RO data has, right? RO data is the read-only data. And which executable should we do this for? Let's do this for the program that we created, right? The Hello World program. That is located at elf/a dot out. All right. Yeah. So this was the file that we were working with, right, in our previous example. So this file, right, and we had this. This is the global var string in it, right? So in your read-only section in the elf, right, in the final executable, you have, look at this string, right? This is the global var, and then you have 69 as well, right? This is what is stored in the actual section. So right. So what this readelf utility did is essentially it went to the file header, located the where the section headers are stored, went to the section header table, found the correct section, which was correct section header, which was .ro data, right? That section. Once it found that section, it used that section header to go and actually find the data and find the position of the data and the amount of data that needs to extract, right? And then it finally went and extracted that much, right? And gave us a hex dump of it. So these are the addresses, and then this is the hex value of it, and this is the ASCII representation, right? So this is what is actually this is how your file is actually, stored in that, your data is actually stored in that file, right? So yeah, so till now what we've seen is essentially the file header, right? Section headers and sections, right? That's what we went through right now, right? So you have a elf header, which essentially points to like program header and section header, right? So what we did is through elf header, go to section header. Through section header, you can go to different sections to actually get the data, right? Now you understand the flow that's going on here. Now there's another thing that we can do is essentially go to the program header table, right? So from the elf header, you can go to the program header. And just to show you here, you see this ph off entry here. So this is the program header offset, right? So that's where you can go. So if you go to there, you land at the program header table. What does that do? Oops, I should go to the next one, and I should do this. So this is the program header, right? Now, if we do it for, let's do it for Win, right? Readelf -l, I believe. Yes. So now, if you go to the program headers, we get this output, right? Where it essentially tells, okay, you can load these things into memory, and what a program header is and why it's needed and stuff. I'll get to that in a bit, right? So just hang on with it. I'm just telling you what exists right now. Why it exists, I'll tell you, right? You can load certain program certain segments you can load, right? So this is a program header, which is essentially the segment header, right? Two different names for the same thing. So with the segment header, what you can do is it tells you, okay, the type is load, so you can actually load this into memory. This is dynamic stuff. So during runtime, if you need something, there's stuff here, and then it also has flags for permission, right? R stands for read, W stands for write, and E stands for execute, right? So yeah, this is how your loader is able to figure out, okay, what do I have to load in RAM? These load segments, right? Everything else I don't have to load in RAM, right? So that's how you have to figure out which segments are to be actually put into RAM, right? And then it sees, okay, which sections can be modified, which sections can just be read, and stuff like that, right? So that is what the segment header has, right? And what a segment points to essentially is just a collection. So this was the segment header, right? The program header, same thing. So what this header is pointing to are segments, right? And what do segments have in them? segments are just a collection of sections, right? So if you see this section to segment mapping, on the left, you see this number. This is just the segment number, right? So the first segment points to this particular sections, and each segment can have like multiple sections, right? And it's grouping things together based on logically similar things, right? So if you see data and BSS, both have variables, right? That we need. So both are in the same segment, right? Dynamic has its own thing and stuff like that. So there are different segments, right? So segments are just essentially mappings of multiple sections which are logically similar, right? So it's just something to wrap them together, logically similar sections, right? So now we essentially know, okay, what is a file header, what is a section header, what is a segment header, what are sections, and what are segments. Now, why is all this section segment thing going on? What is all of this and stuff like that, right? So now what we get into is there are two views of an ELF file, right? So the same file, depending on who's looking at it, can be looked at in two different ways, right? One way is the linking view and one way is the execution view. It is important that you understand that the same file is being looked at in two different representations, right? They're not two different files or anything. It's the same file, same bytes, just looked at in different ways, right? So when you talk about the linking view, that's how the linker interprets the file, right? And for linkers, it's all about sections, right? Each individual section, it has to do something with each section. That is why it is that way, right? With the execution view, right? With the execution view, that is where the loader looks at it, right? Which segments do I load into RAM, right? And which segments I do not, or where is the dynamic segment, right? So that's the difference between the two. So yeah, it's the same file, just who's looking at it, who's handling the file right now is how it is interpreted, right? Same file, right? And I'm stressing on that because I was super uber confused on this for um, quite some time, right? So the linking view of the file, right? What is essentially going on here? There are a few sections that you can look at that we've seen before, right? The text section, which is essentially where your instructions are stored. Data section where your is where your now here is where I tell you why there are two different sections, right? Like when we were looking at the representation in RAM, we're like, okay, both have variables. This one is uninitialized, initialized to 0, and one is initialized with whatever value you gave it in data, right? Data segment has initialized, BSS has uninitialized variables, which have now been initialized with 0, right? So what is going on, right? Why is it this way? So the reason is, in an ELF file, when you're linking it, right? When you're linking an ELF file, in the BSS section is essentially where let's say you're allocating an array of 5,000, right? Where you don't give it data, right? It's just you just say int array 5,000, right? So you won't want to put 5,000 integers into an array, but you're not actually giving it any value, right? So why should the ELF file occupy 5,000 bytes? Why should that variable when stored in the ELF file, why should it occupy 5,000 bytes when it's uninitialized, right? That's crazy. It's a different thing if you've been like int array 5,000 and you actually provided 5,000 values, right? That's an initialized variable, right? So that initialized variable occupying that much space, right? Those 5,000 bytes or 5,000 into whatever 4 bytes or whatever, right? That occupying that much space makes sense. But if you just say int array 5,000, that should not occupy 5,000 bytes because it's uninitialized, right? So what the ELF format does to handle this is essentially it says, okay, you want an array of 5,000, but you have not given me any values for it right now. So what I'm going to do is I'm just going to, instead of it occupying whatever 5,000 into 4 bytes, right, 20,000 bytes or whatever, I'm going to just let it occupy a few bytes, which help me describe the variable itself, right? So instead of occupying 20,000 bytes, something like that, you just occupy, let's say 40 bytes, right? So it tries to save space, okay? So that is why the BSS section exists, right? To save space, okay? Now, For data section, that obviously every variable in there, because it's been initialized with the value, it occupies the value that is been statically requested, right? So if it's int array 100 and you provide 100 values, it's going to occupy 100 into 4, 400 bytes, right? So yeah, every variable in the data section is going to occupy the amount of data that you request for, but every variable in the BSS section is only going to occupy the amount of data required to describe the variable itself, right? So instead of 20,000 bytes, just 40 bytes, right? That makes a lot of sense, right? So that is why essentially we have those two different types of segments, right, later on, because they were essentially created this way in the section, right? So by linking, you look at it this way as data in BSS, right? This is the logic behind it. So which is why later on in the execution, we also have to treat them separately and sort of handle them separately, right? So yeah, and there are other symbol tables and relocation entries so that the linker can essentially figure out, okay, where is this particular symbol? So if you say printf, right, where is printf? How do I find printf, right? So the linker is able to add some information. Hey, it's in this library, it's at this particular location, and it's able to properly link all of that together, right? So symbol table relocation entries are things for that, right? Right, as I mentioned here, used by linker to resolve symbols and relocate data, right? The next thing that we can look at is the execution view, right? This is where this is how the loader looks at it, right? And it is just clubbing a few sections together. Sorry, Varsha had a question. What happens if some part of the memory is initialized, other parts uninitialized? Does So whichever variables are initialized, they go in the data section, and whichever variables are uninitialized, they go in the BSS section, right? And now when they now I'll cover this now. So now when you have these segments, right, in the execution view, when the loader is actually loading stuff into RAM, whatever it sees in the BSS section, now it will allocate it memory, right? And it'll be like, okay, you asked for array 5,000, int array 5,000. Okay, now I'm going to give you 5,000 bytes in that BSS segment, right? So the BSS segment will occupy as many bytes as statically requested, right? But the BSS section, that will not occupy 5,000, 20,000 bytes, right? So yeah, do you understand that, Bhavesh? So in okay, great, awesome, got it. And as I told you, not all segments need to be loaded into memory, right? There are certain segments which have the type load. Only those are loaded in memory, right? So yeah, those are the two views of the same file. Okay, when the linker looks at it, it looks at it in the form of your section header table and sections, right? Excuse me. And your execution view, when the loader is looking at it, it looks at it in the segment form, and there's a segment header table that it looks at, right? Okay. Yeah, elf parsing demo is essentially me just showing you this the program that I built, which is called pelf, right? Essentially it just parses whatever files you have, whichever. If you give it an elf file, it'll give you the file header, right? It'll give you the section header, all the section headers, and it'll also give you all the program headers. And one thing that I did add, just because I wanted to explore, I wanted to see how does a linker or a loader figure out which dynamic libraries does this file depend on, right? So there's a dynamic section that you can go to and you can figure it out, right? So I wanted to show you one thing. Let's examine the Vim binary, right? So if I give this to my program, right, we can see that the Vim binary depends on these 1, 2, 3, 4, 7 or 8, whatever dynamic libraries, right? And all these are shared objects, right? So all of these are dynamic libraries. Now, but if we use something called LDD, right? Your LDD is a particular utility in Linux, which will tell you which dynamic libraries does a binary depend on, right? So if we go to LDD, you suddenly see so many lines, and I was shocked. I was like, okay, my program is giving me just these many dynamic libraries, and LDD is giving me these many, so many. Why? What's the difference, right? So if we see all of these here, libm to libc, all of them, you can see here, right? But then there are certain extra ones. So what's going on essentially is each of these libraries that are listed here in my program, have their own dependencies. So what LDD is doing is it is listing out each of the libraries that are located in the ELF as well, but it also checks for each library, do you depend on each one, right? Because each shared object is also an ELF, right? As I'd shown you before, each shared object is also an ELF. So it goes into that ELF and figures out its dynamic dependencies. So it's just listing out all those outputs, right? So what I did is was just for one ELF file, right? So imagine going to each ELF file and parsing its dynamic libraries and printing that. So LDD is just a recursive function on what I have done, right? Which is why you see more files here, right? And libraries like VDSO and LD that you see here, right? LD and VDSO, these are always added to every program, right? They are required for interpreting and stuff like that. LD is, I think, the main linker that Linux uses. So, which is why it is always added, right? So, yeah, that is. I just wanted to tell you why if you use my program, you get lesser stuff, and if you use something like LDD, you get more, right? Because LDD is just recursively doing what I did for one file, right? So, okay, that was one. That is what I wanted to show you. If you want to, oops, yeah, if you want to check this project out, it's on GitHub. I should probably use this. Right, it's on GitHub. It's there's a lot more. There's a lot of stuff going on there to make this work. It was a painful process that took a few months, but fun one. And yeah, and also with the compilation stuff that I showed you before, there's a lot more stuff where actually get into using where you like I actually explain what is going on here and stuff like that, and also use the linker called LD to actually dynamically link each and every library, right? Because essentially even what we see with GCC, right? It's just very high level. So if you actually go and use the linker that Linux itself uses, you have to tell it, okay, I'm using this library, and then to link your final program, which is your where are you? Your actual main.o, you have to include some libraries before, some libraries after, and stuff like that to actually make the linking process work, right? So yeah, it's quite some stuff. You should go and look at this as well. There's a lot of stuff going on in the backend, right, that I didn't talk about in the talk. So okay, now I think the last part is remaining, which is pretty simple. We already saw most of this. Okay, so file utilities, right? So just getting used to how files work, right? This is the last part of the talk. Just bear with me, right? So if you have a file, right, how do you inspect it? What do you do, right? How do you actually figure out what is going on, right? So there are certain commands that you should kind of be aware of. The ones in yellow are usually the important ones or commonly used ones. So file, we already saw file. You can just get an output about the file. We saw it multiple times this time, right? Size, it will just tell you what is the size of your binary, right? And different sections in the binary, right? Like what is the size of your data section, BSS section, text section, right? Just to show it to you, if I give it my binary, right? So it tells me, okay, your data section, your I think this is the overall file size, and then these are broken down, right? Like text section is this much, data section is this much, BSS section is this much, right? So that is what size gives you. Object dump, it's not installed on a machine. I don't know why, but essentially it will disassemble files for you. The output that we saw here. Oops, compilation examples. So the output that we saw here, this is object dump disassembling this file, right? It does a bunch of things more. It's a very helpful command. Readelf, we saw that multiple times to display different sections of a file. We can just do, like, if you want to look at the program headers, you use -l to look at that, right? So readelf, very good to examine the contents of an ELF file. LDD, we saw that it recursively lists all the dynamic dependencies of a particular file, of a particular ELF file, sorry, or an executable, right? strace is used to trace system calls made by a particular program. Again, to show you a demonstration, okay, not right now, maybe. XSD, we saw hex dump, right, to get the raw output of thing. You can use hex dump or XXD. They do similar things, right? So if I just give it my program, right? This is the hex thing that we use, right? XXD or hexdump. GDB is a debugger, the GNU debugger. I personally don't have enough experience to use this, but it's very useful, right? I've not used it much though, unfortunately. NM is, I forgot what NM is. Um, okay, it lists symbols, right? Yeah, symbols are essentially function names, global variable names, things that stuff that you refer from different libraries, different files, right? Different header files. Those are symbols. So NM will be used to list those. Now, I don't know if this is going to work, but I'm going to try. Okay, right? These are all the symbols, right, in the file. You have main here. You should have other things as well. Yeah, elf magic bytes is something I've used in my code, by the way. So that is why it's a symbol, right? Because it's, so if you see, I'll just show you quickly. Parself in the header file. In the header file, if you see this, elf magic bytes, right? So, and then you see this in the symbol output, right? Elf magic bytes. So yeah, this elf magic bytes is a symbol, right? Because it's a global variable in my header file, right? So just some correlation to show you, right? So yeah, NM is used for that if you want to inspect symbols and stuff. Ltrace is similar to strace, but ltrace looks at library calls. Strace looks at system calls, syscalls, and ltrace looks at library calls, right? I'm not going to demonstrate that. I don't have enough experience with it. Strings will essentially just print out all the strings in the file, right? So if you do strings and this binary, you'll get all. Oh yeah, so Alpesh, you are right. It gives you everything, right? Literally every string in the raw binary that it can find. Yep, everything, load, everything. Any text string that it can find, it just prints that, right? All function names as well. So if you see this parse L64P address, that's a function that I defined. Here is our elf magic bytes again, right? So any string that it's able to find, right? In the raw output. So yeah, strings does that. File compilation, it's mainly GCC. We already saw GCC. With LD, I showed you that there are, there's a particular way in which you link files, right? And GCC just does that for you. When you do GCC-C, GCC literally just links it for you, right? Instead of you having to do it manually, right? So LD is the low-level command that you can use. Then AS is assembler, right? Instead of using GCC-C, you can just do use AS as well, right? That's the GNU assembler. It's also called GAS, right? Then for file manipulation, this is strip, right? So if you remember initially when I showed you the file outputs, I had mentioned that, okay, bear with me, I'll tell you later. So if you see this, not stripped, stripped, not stripped, not stripped, and here there'll be someone which is stripped, not stripped, right? So that is what this utility can do for you, right? Stripping. What stripping essentially does is it will remove all the symbol files and stuff like that from your output, right? All the symbols or unnecessary things, right? So if I strip pelf, right, let's see what that did with strings. I'm not sure how much difference you'll be able to notice, but yeah, I think the output is significantly reduced, right? Loads of these, like instead of it being such a long output, right? There's these so many DS handle, Gmon start and stuff that's all absent from here, right? It's just this much the output, right? So it's all removed all the unnecessary symbols that it doesn't need, right? That's what stripping a binary does. It reduces the file size, right? What we can try to do is we can look at oops, we can look at this, right? So we have a.out, right? Let's see the size of a.out now, and let's strip it and then see the output, see the size. And now if I check size, 8, okay, does not reduce, my bad. Interesting. But yeah, it removes symbols and stuff like that, right? Editors, Vim Nano, you've seen me use Vim all the time for the entire duration of this talk. Really nice. DD, the only reason I kept it is because it's a little funny. DD stands for copy and convert, right? So it should be CC, right? But essentially what happened is that copy and convert CC stands for C compiler on some Unix systems. So instead of using CC, they went to DD for copy and convert, right? So just the next alphabet. So instead of CC, it became DD, copy and convert. Then change group, change owner, and change file permission bits is something that we've all used quite a bit. Just wanted to include that in there. And with that, that concludes the talk. I hope you understood more about elves. And yeah. Oh, one thing that I wanted to talk about was statically and dynamically linking, right? So if so, okay, I'll not execute this. I'll just show it to you so that we can save some time, right? Okay, so we have two files, right? Main.c that we had, right? We're just going to add this static flag to it, right? And send the output to a file, right? And we're going to normally run the file gcc main.c, right? So if we go and compare the sizes of the two, the static file is this size. But if we check the normal dynamically compiled file, that's just 2046 bytes, right? So the static binary, all of the like functions that you refer to from different libraries are put in the file itself, in the executable file itself, right? Which is why this file becomes so big, right? But in the dynamic case, it'll resolve that at runtime, right? When you say printf or some particular function at runtime, it'll go to libc and figure it out and do it for you, right? So that's why the binary is so small. You can clearly see the difference in that small main.c program that we wrote. This is the difference, right? Crazy difference between the two files, right? So, but there are advantages, disadvantages to each one, right? With a statically linked binary, no matter what dependency changes, no matter what library changes on your thing, your code is going to run the same every time, right? But it comes at a disadvantage that your binary size increases a lot, right? With dynamic linking, the advantage is, okay, your binary size reduces, right? And if there's a version change in a library or anything, any newer, or if there's a bug in the library that or a critical security issue and library has to be upgraded, it can happen automatically, right? You don't need to essentially recompile your file, right? A system update can resolve that. You don't need to push an update for your own software if it's dynamically linked. But the problem with dynamically linked libraries is if that update to that library breaks the library, your executable also breaks, your program breaks, right? So both have the advantages, disadvantages, depends on your use case, right? It depends, right? So yeah, that's the difference between static and dynamically linking something, right? At a high level, obviously. So yeah, and with dynamic linking, there is something more called load time dynamic linking, runtime dynamic linking, and stuff like that, right? But yeah, I'll leave that for some other time when I also have more knowledge on it. But yeah, that concludes it. The entire talk and everything is essentially written down in a detailed format, right? Everything that I told you is written down properly, explained properly at this place. So in case you want to go over this entire talk again, everything is written down for you, right? With pictures, outputs, everything, right? All the utilities that I explained, everything is written down here, right? So, and if you want to do your own digging, there are resources that I used as well, right? So everything is written down here. Let me know if you have any questions or anything you want to know. Yeah, thank you so much. Any questions, anyone? How to edit an ELF file? What do you want to edit essentially exactly in ELF file?
Harsh, I have like a small question posted in the chat एक बार देख लो.
Okay, any other questions, anyone? Sure, take your time out.
Yeah, I have one. What existed before the ELF file?
Okay, awesome. Thank you so much.
Hello?
Can he hear us?
Harsh, you cannot hear us.
Hey, Pranav, you there?
He thinks everybody's quiet.
Oh, I can't hear you? What? I think I can. Oh, interesting. I'm sorry. Oh, I finally can hear you now. I'm so sorry. Were people saying something when I was talking?
Yeah.
Yeah.
You point blank ignored Siddharth.
Oh my
And
god.
me.
Wait, how many times did I miss people?
I
Twice,
think
twice. Just Siddharth and me. Yeah.
Yeah, Siddharth and Dheeraj.
Okay, thank God. Any questions, anyone? I'm so sorry. I didn't know. So
Siddharth
sorry.
had a really interesting question. What existed before ELF files?
I'm not sure. I'm not sure. The only thing I know that A.out was the official thing before, but what format it followed before back then, I don't know.
Okay. All right.
I have
Just-
a
I
few interesting links to share about that, about the history of it.
Okay.
We'll do that.
Will you? Yes, please. Awesome. Is Pranav here?
yeah, Pranav is.
Awesome. You can stop the recording, Pranav.